Okay, good morning everyone. Today we're gonna start a new chapter 17, wave optics. And then before we talk about, let me talk about the light first. Light is very special, thing you will see. So first question is what is a light, right? Under some circumstance, light acts like a particle. And then sometimes, because it travels in a straight line, right? So like you sometimes, people assume light consists of small particles, right? So then, if you have a flashlight, passing through a small hole, light goes this way, right? It all goes, right? So that you can also assume, small particles are traveling, right? But sometimes light shows the same kind of a wave-like behavior like a sound wave or water waves. So sometimes, people think light is a wave. So these two properties light has, and then sometimes they have a particle property, sometimes they have a wave property. So the question is the light particle or wave? And the answer is the light has a both properties, which is very strange and special. Because in general, if you have an object, object is object. In other words, particle is particle. And the wave is wave, right? So change the circumstance yet again, and the light exhibit behavior that is neither wave-like nor particle-like, but has a both of them. And then we developed three models of light in this section, and you will see one by one. The first one is, as I said, in the wave model. You know, many circumstances light exhibit the same behavior like a sound or water, right? The bright colors of a hummingbird and then the blue of the sky are best understood in terms of the wave model of the light. Some aspects of the wave model of the light were introduced in earlier chapter, right? In terms of sound things, right? So the wave model is a primary focus of this chapter. Okay, so that this chapter 17 is mostly about the wave property of the light. Okay, and the ray model, properties of a prism, mirror, lens, any other optical instrument, are best understood in terms of a light rays, straight line path that follow in that line follows, the light follows, right? And then we call it ray optics. But ray optics is basically part of the particle property of the light. And the third one is a photon model. Photon is the name of the light particle. And then we call it photon. In other words, light consists of photons that has a both wave-like and particle-like properties, but it's more like a particle-like properties. And the photons are the quanta of light. Okay, but we'll learn about this later. So now let's talk about light properties in terms of its waves. So the very first thing is called diffraction. So now before we start talking about light, let's start talking with the water, which is obviously a wave. So assuming a water wave passes through a window like an opening in a barrier. So this is your openings. And the water, basically a front wave of the water is traveling from here. And then see this opening, small hole. And then you will have a barrier here, wall here, right? And then obviously everybody know, right? The wave spreads out, right? So you see something like this, right? The wave spread out, right? And then this phenomenon, wave spreading out property, is called diffraction. So diffraction is a clear sign that whatever is passing through an opening is a wave. In other words, diffraction is the one of the most important property of wave like water has here. Water is wave, right? And then we're gonna invest the same property of the light. But now you see, before we talk about light more, you can also see when the opening is many times larger than the wavelength of the wave. So especially the hole size is greater than previous, then you see this diffraction pattern, even though you still see this spreading, right? You still see this spreading out, but that's not, you know, straightforward and obvious like here. So the diffraction you see is very clear, especially when the hole size is very small, right? So this is a similar. So now we can do the same thing for the light, right? Similar to the straight line appearance of the light with the sharpest shadows as light passes through the large window. So you see large window, light passes through, and then you see there's no spreading out. The shadow area here, especially, it's very clear, right? The dark area and the light area, the boundary is not clear, right? See, as you see here, this is the shadow area, which is not clear when the hole is big. But again, this shadow area here and here, when the hole is small, it's not small. So in other words, you can say diffraction, you can observe diffraction clearly, especially when the hole size is small. Okay? And another, important thing that you will learn later is the light is an electromagnetic wave. So, if you learn physics 2, the most important, you will see later soon, right? So, two important wave is electric field and the magnetic field. The electric field is basically generated by, current, and the magnetic field is of course generated by, normal magnet, right? And then these two generate each other. And then the combination of these two is the light. So in other words, light consists of a very rapidly oscillating electric and magnetic field. And we call it electromagnetic wave. And the electromagnetic waves travel in a vacuum at a speed of the light, which is a 3 times 10 to 8 meter per second. And the visible light, everybody know, ranges from 400 nanometer, 700 nanometer, right? Wavelengths. So this is a blue area and this is a red area, right? And then because the wavelengths are very short, the frequency of the visible light are very high. Why? Because again, your velocity of the light, which is 3 times 10 to 8 meter per second, is fixed. Again, velocity is a wavelength times a frequency. So then, for short light, short wavelengths, blue ray, lambda is a 400 nanometer. Then it has its corresponding frequency. Same for the red light. So you can always find, frequency of the light if you know wavelengths of it. So for example, 600 is kind of a green, something like that. So then you have a velocity 3 times 10 to 8 divided by its wavelengths will give you frequency, and you see the frequency is a really high number, right? And the next thing is the index of refraction. So light waves slow down. So the 3 times 10 to 8 meter per second is the speed of light in a vacuum. So if the light, moves, passes through an object, it basically slows down. Okay, such as water, glass, air, whatever. As long as it's not a vacuum, their speed is less than 3 times 10 to 8 meter per second. But this is due to the interaction between electromagnetic field of the wave and the electrons in the material. The speed of light in a material rather than vacuum is characterized by the material's index of a refraction n, which is defined as a speed of light. So it is a c is a 3 times 10 to 8 divided by speed of light in that material. So then this v is always smaller than 3 times 10 to 8, right? This number is always bigger. So n is always greater than 1, and especially when b equals c, which is 3 times 10 to 8 as well, and which gives n, so that means n of a vacuum is 1. Right? This is a typical index of refraction, right? So vacuum 1, air is almost like a vacuum, so slightly higher. And then you have water, glass, diamond, but you don't need to memorize any number of this except the vacuum is a 1. Right? So the frequency of a wave does not change as the wave moves from the one medium to another. So the frequency is kind of a intrinsic property of a wave. For example, red light, its frequency is always 800 nanometer, even though it passes through materials like glass or whatever. So wave is the same, the wavelength is the same. So, but now you see velocity is a wavelength times the frequency. But now you see this velocity is changing, especially slows down, especially when it passes through certain materials, right? So then in order to decrease this number while wavelength is a constant, what do you need? You have to have a frequency down, right? So the wavelength must change, right? Sorry, but the frequency does not change, right? Frequency does not change, so frequency is a constant. Sorry about that. Yeah. Frequency does not change. So this is a constant. So the wavelength must decrease as well, right? So in general, your frequency, sorry about that. So red light has a smaller wavelength, right? In especially in other materials, right? So then if, as you can see in this picture, right? Vacuum wavelength is this long, and later your wavelength gets smaller and smaller. So that means you have the same frequency. Frequency is constant, so wavelength is decreasing. So your materials wavelength is simply vacuum wavelength divided by n. Again, n is greater than 1. Right? So the wavelength in the transparent material is shorter than the wavelength in a vacuum. So you can remember, these pictures, right? So the light wave travels as a plane wave. Air is almost a vacuum into a glass 1.5, which diagram shows a collect wave front. So again, wavelength is getting smaller. So the answer is C. Right? And then orange light with a wavelength of 600 nanometer is inclined in incident on a 1 millimeter thickness of glass, right? So then now you have a 1 millimeter thickness glass, and the light 600 nanometer is traveling, orange light, right? And then what happened? How many light speed in the glass? What is the light speed in the glass? So then you see light glass, the speed will be decreased by the n of the glass, right? Which is 1.5. N of glass is 1.5. So your speed is gonna be 3 times speed of the light in vacuum divided by 1.5. So the velocity or speed is 2 times 10 to 8 meter per second. And the second question is how many wavelengths of the light are inside the slide? So basically we want to zoom in this glass, right? So this is basically 1 millimeter. Let me zoom in. This is a 1 millimeter glass. And then now the wavelengths. So then next question is what is the wavelength of this orange light in a glass, right? So then this will decrease by factor of n, right? So your new wavelength is 400 nanometer, right? So that means now you have a wavelength, boom, boom. Sorry, first one is 400 nanometer, and the other one 400 nanometer. The other 400 nanometer, right? So your answer is simply 1 millimeter. Then you gotta convert it to meter, divide by 400 nanometers. So your answer is 1 millimeter divided by 400 nanometer. So then you see 2500 nanometer. So that is the number of waves in the glass. Right? Okay, thank you. Next time we'll talk about two important experiments, double slit experiment and single slit experiment. Let me know if you have any question. Thank you.